Erik Curiel, who was also here for our best workshop on web tools. I'm really very happy that he is here again today. He's a senior researcher at the University of Bonn in the backbone and he will talk about geometry, gravity, matter, and the dark energy.
So, thank you very much for having me back. It's always a well, I should rather say so far. It's always been a pleasure to come to the track. And I guess I think won't give my normal preparatory remarks. I'll just jump right in. No, I will say one thing. I lied. So there are actually many more slides in this document that I plan to discuss. That's because I included a lot of technical material, which I just plan to skip over while I'm talking. But we can return to during Q&A if people have questions. So it'll be clear what I'm skipping over, and you can come back in Q&A, I think. So yeah, so we're gonna try and cover a lot of ground here today. I'll just I'll set the stage. I'm going to consider several different attempts to give a criterion for distinguishing geometry, gravity, matter, and none of them really work. And then, very unusually for me, if anyone who knows me, I'm actually going to try and do some metaphysics, but I'm going to try and do it the right way. So first, I'll be considering the idea of substance versus accident in GR. And then I'll be considering the role of stress energy. So Antonio and everyone else can beat up on me for this. And a deeper analysis of what it means for different kinds of physical systems to couple with each other. And I will end on an aporia about dark energy. So I can never resist quoting one of my great heroes, James Clerk Maxwell. This is from his article "Attraction" in the ninth edition of the Encyclopedia Britannica from 1875. If y'all have never looked at the 9th edition of the Encyclopedia Britannica, you totally should. It's fucking amazing. The people they got to write articles. I mean, Maxwell not only wrote the entry on attraction, he wrote the entry on atom, on molecule, on several other things. They had Kelvin. They had Boltzmann. They had Alfred Lord Tennyson. I mean, they just had like the most amazing 19th century people write entries in this encyclopedia. Go check it out. Anyway, I don't get money from Encyclopedia Britannica. So he's talking about what we might consider a metaphysical question. What does it mean to say possibly that two physical systems act at each other at a distance? Which clearly in the 19th century was a very live, important issue. We must bear in mind that the scientific or science-producing value, I don't have to look that way, do I? No, that's too small. Made to answer these old standing questions is not to be measured by the prospect that they afford us of ultimately obtaining a solution, but by their effect in stimulating men to a thorough investigation of nature. To propose a scientific question presupposes scientific knowledge, and the questions which exercise men's minds in the present state of science may very likely be such that a little more knowledge would show us that no answer is possible. The scientific value of the question is the cosmological constant matter or gravity or geometry is to be found in the stimulus that is given to investigations into the properties of field theories in general. So just keep that in the back of your mind. It will become, I hope the relevance of it, if it's not already clear, it will become clear by the time we reach the application. So in this talk, so just a very few things just to say to set the stage. So in this talk by dark energy, I really just mean flat-footed cosmological constant in GR, not any of the commonly considered alternatives or even the more exotic, research niche alternatives. And since I'm not going to discuss any of these, I'm not going to read the list. And anyway, the first speaker, and since I'm going senile and terrible names, I'm terribly sorry, I cannot remember your name. The first speaker did a wonderful job of already discussing this anyway. So the main puzzle, I take it, for the purposes of this talk and in part the workshop, is how to determine whether the cosmological constant is matter or geometry. How do we distinguish matter from geometry at all in GR? And from here on, even though Niels apparently doesn't like it, I'll use left-hand side, right-hand side, LHS and RHS, to refer to the sides of the EFE, meaning respectively geometry terms and matter terms, just for brevity. So this. So why is it of interest anyway to distinguish geometry from matter in this context? Well, a few reasons, just to give us some motivation. We may want to treat the terms differently in attempts to modify or extend or quantize a theory. It may provide deeper understanding of the conceptual structure of general relativity or gravitational space-time theories more generally. It may provide deeper understanding of the nature of the world itself, depending on your philosophical predilections about these things. I think actually it also bears on the issue of the status of the equivalence principle. This will come up later, because for instance, do test bodies follow geodesics of some appropriately privileged affine connection on space-time? Well, if what we may want to think of as new geometry terms are really this, stress energy of exotic matter, then yeah, there's no reason they shouldn't if it's really GR. Otherwise, in general, actually, no, they won't. And so this might actually give us a way, in principle, but either to distinguish matter of geometry, or if we're careful in our testing, or to also a way to test the equivalence. If we find failures of the equivalence principle, it might give us guides in trying to figure out why we seem to be seeing failures of the equivalence principle. So I think, yeah, that's basically all I want to say to such a scene. So let's jump in. And I'm now going to say something about the equivalence principle as it turns out. I think that actually standard versions of the equivalence principle already suggest some blurring of the line between matter and geometry or gravity. I'm being agnostic between the two right now in GR. So, one formulation of sometimes called the weak equivalence principle is gravitational mass equals or is the same as inertial mass, which means that the property that sources geometry is the property that is guided by geometry, speaking very loosely. But geometry, of course, in GR, we know can, in some sense, sort itself. We have non-trivial vacuum spacetimes. And geometry can, in some sense, guide itself. It's, it's the metric that we use to determine the characteristics of gravitational waves that we use to characterize their propagation. So at least at this level, there doesn't seem to be much difference, at least trying to use this, thinking about these issues, there doesn't seem to be much difference between geometry and matter here at all. And one might even think if one moves to a stronger version of the equivalence principle, or the Einstein's version of the equivalence principle, or Jesus, there are so many versions of the equivalence principle. But let's not worry about that. Just something stronger than gravitational mass equals inertial mass, or all bodies follow the same paths irrespective of their mass and composition when they are not subject to any force except for gravity. One might think that a stronger version of the equivalence principle says something like the following: in the presence of an effective gravitational field, even when no matter is present and the system is only accelerating, if one can say that, given the equivalence principle, that may suggest, again, that the difference between matter and gravity is perhaps not wholly conventional, but perhaps better only effectively determined in the sense of an effective field theory, at least according to some quantum gravity and some semi-classical gravity programs. So it's not really clear to me whether we can really get any mileage out of the equivalence principle. So I'm going to put it aside. I'm going to put the equivalence principle aside. In general relativity, if you don't think very hard about it, which sometimes is a virtue about trying to make progress, there's a kind of obvious answer to the question: is something matter or geometry? And that's given by the way that what we naively think of as matter and geometry couple to each other via the Einstein field equation. If I know the stress energy, which is a property of matter, naively considered, then I know the Einstein tensor, and so I know the Ricci tensor, and I know I don't know the Ricci scalar because apparently the Ricci scalar is no longer part of the Einstein field equation. Y'all probably didn't realize this. General relativity has now changed. This is actually the Einstein tensor. No, I'm kidding. You get the Ricci tensor, and so you know the scalar curvature if you know the stress energy. And if there's no stress energy, there's no Ricci curvature. And so matter is whatever's associated with Ricci curvature, and gravity is the free gravitational degrees of freedom are encoded in Weyl curvature, which is what's left over. So that's unsatisfactory for several reasons, though, actually, in fact. Because, again, I'm going to use the terms matter and geometry somewhat naively, since I haven't given you a way to distinguish them in any principled way yet. Because, in fact, both matter and geometry, naively speaking, can constrain geometry. Again, geometry can sort itself, non-trivial vacuum solutions, but different types of geometry, different facets of space-time geometry can non-trivially constrain each other in ways not mediated by, generally speaking, by the Einstein field equation. So, causal structure and topology can by themselves place series constraints on affine structure. Think about most of the singularity and black hole theorems in vacuum spacetime. Causal structure and topology can, in conjunction with matter, place constraints on the affine structure. Again, singularity and black hole theorems in non-vacuum spacetimes. In fact, if you think about every single type or aspect, however you want to think of it, of spacetime geometry, causal, topological, projective, conformal, affine, curvature, metric, every single one of them, there's a really whole subtle interplay of relationships among them. And the way they each place constraints on, the way that they variously place constraints on each other is really fascinating. And they do so for the most part independent of the Einstein field. Most of the really independent ones I know of, they do so really independent of the Einstein field equation and of matter. So one might think that if something characteristic about matter is it constrains curvature, well, that again doesn't really distinguish it from geometry itself, and even in fact from when one distinguishes different types or facets of geometry in the broad rubric of space-time geometry. So let's try another approach. Let's think about the differences in their respective symmetries of local degrees of freedom. So, okay, one might say, okay, great. I know that my matter fields, and this comes out most clearly, say, if I'm thinking about quantum fields, the dynamical degrees of freedom of each type of matter field comes canonically with a canonically singled out set of symmetries that is captured by a characteristic group. And generally, one looks for irreducible representations of some group to get the particle zoo. And maybe this will be a way to distinguish if I can figure out what all the local degrees of freedom are in some region of space-time. Then maybe I can distinguish what are the matter degrees of freedom from what are the geometrical degrees of freedom by looking at the characteristic symmetry groups that the different degrees of freedom are constrained by. For leptons, the group generally is SU2 or U1, or maybe some semi-direct product thereof or direct product thereof. For hadrons, you throw in an SU3 because quarks are funky, and so gluons for that matter too. And the same for exchange bosons. One may want to say That in GR, for local gravitational degrees of freedom, the symmetry group is just, the Lorentz group, 013, or if one restricts to if one doesn't like time reversals and parity reversals and one doesn't really care for null screw, four null four screws composed with spatial translations, then you might restrict to the proper Lorentz group, SL2C. And so great, it looks like things are looking pretty good because we do get different groups associated with different local degrees of freedom for different things. But you really have this clean separation you really can say this for gravity only when there's no matter present. Because when there is in fact matter present, and you really try and work out, say what the transformation group of the Weyl curvature is, for the Weyl tensor, it turns out that you actually get the groups kind of mixed. And so you can't actually use this criterion to know what groups apply to which degrees of freedom unless you already know the distinction between matter and gravity. So this doesn't quite work either. Okay, let's take a page from Einstein, Harvey Brown, Hermann Weyl, David Malamud, and say, okay, look, here's a distinction. We use matter to operationalize geometry. And if you're Albert or Harvey, then you like rods and clocks. If you're Hermann or David, you like paths of light rays and massive particles. But I actually don't think that in the end really cuts in the ice either, because as far as I can see, this is not a principled restriction. This is not a principled asymmetry. It's just that using rods and clocks or using light rays and massive particles is just how we know what to do, given limitations on what we know about gravity and general relativity and our quite limited technical expertise in constructing systems that one may want to think of as purely gravitational or purely geometrical. I mean, I don't see any principled reason why we can't use Wheeler's geons and gravitational radiation to operationalize rods and clocks. If you give me, I think, 2 weeks, and by giving it 2 weeks, I mean like pay my salary and give me lots of nice bottles of wine, then I think I could probably sit down and work out like how to represent rods and clocks using geons and gravitational waves. It'd be very crude. It would be almost impossible to really make sense of in any kind of experimental way. But it's not. It's a technical problem. It's not a conceptual problem, so far as I can see. So I don't think this works. And then there's a few difficulties and problems for the whole idea that is based on the idea of fungibility. We generally think that things are of the same category, of the same kind, if we can transform one into the other. And it seems, again, having this naive conception, this naive distinction, of pre-theoretic distinction, if you like, between gravity and geometry and matter. Well, if you look at quantum effects in gravitational fields, like the Hawking effect or particle production in cosmological models, you get what looks very much like. I think it's actually quite fair to describe as geometry is transforming into matter. In gravitational collapse, it looks like matter is transforming in the geometry. The matter vanishes into the central singularity in classical GR. You can have some rather exotic spacetimes, but since we're exploring the conceptual structure of general relativity, I think I'm allowed to use that. Do you have any objections?
No, fair fault.
So consider the following example. So take your favorite vacuum, globally hyperbolic vacuum spacetime. And 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 fix some Cauchy slice on its sigma. Well, we know by the Choquet-Desroches theorem that the maximal that the maximal Cauchy development of this sigma will return either this globally hyperbolic spacetime or an extended globally hyperbolic spacetime that contains this as a proper submanifold. Let's just say it's maximal to start with, so just to make things easy. But now consider the following: just choose some region up here to the future of our randomly chosen Cauchy slice. Slap some non-zero conformal factor onto that, but you choose the conformal factor cleverly so it goes to 1 on the boundary, and it's 1 everywhere else in the space-time. Well, conformal transformations, I mean, so this is not a diffeomorphism. I'm really changing the metric. So GAB is going to 5 squared GAB. It's just that GAB equals 5 squared GAB everywhere except for there. Conformal transformations they preserve causal structure. This is still a globally hyperbolic spacetime, but it's not the one you get from the Cauchy development, from standard Einstein Cauchy development. So, but if you take it seriously, but nonetheless, it's a perfectly respectable Lorentz geometry. I can write down the accent field equation. We know that on pain of violating the Choquet-Desroches theorem, this region can't be vacuum. And in fact, we know that for even simpler reasons. Just compute the stress energy tensor for this new metric, and you're going to get a TAB that has terms like that, just combinations of derivatives of the scale of the conformal factor in the metric. So you're going to have some kind of funky exotic matter in there. Probably doesn't satisfy any reasonable field equation you've ever heard of or can even imagine, but doesn't matter. We're in conceptual structure here. So this is a space-time in which it looks like you're just cruising along very happily with your, everything's vacuum, and then all of a sudden, the really weird exotic stuff just pops out of the vacuum. And then it hangs around for a while, and then it dies away. So it seems like here you might have a case where matter and geometry mutually transform into each other. You might not like that very much. You might think that's not a reasonable description of what's going on. So let me give you another example, another funky example. I'll just do it. So there are certain exotic in the sense that the equation of state for there are certain exotic FLRWs, exotic in the sense that the cosmological fluid filling the model has the equation of state has barotropic index less than -1. You might think it's crazy, but again, we're interested in conceptual structure here. So, and it turns out that for these, I'm now drawing a Penrose diagram of the thing. What we thought of as, scry minus as Hasnell infinity is actually smoothly extendable to Minkowski spacetime. So this seems to be a case. I mean, the extension really is smooth. It's crazy. So this really does seem to be a case where here you're cruising along not only in a vacuum space-time, you're just cruising along in a flat space-time, and all of a sudden this crazy exotic matter just erupts out of nowhere, and you're flying into FLRW. So GR really does seem to allow, in some sense, quite promiscuously, unless you impose further constraints on what your allowable models are. Matter to spring out of geometry, spring out of certain aspects of geometry matter to subside or condense into pure vacuum geometry. This doesn't necessarily.
Erik,
Yeah.
would it violate some energy condition?
Which one? This one or this one?
Well, either.
This one may or may not violate energy condition. It depends on how you choose your conformal factor. If you're clever, you can get it to satisfy every energy condition. And this one, the perfect fluid in here actually necessarily will violate at least the weak energy condition.
Okay. And sorry, you said earlier it was not a diffeomorphism. Did you mean not an authority, or why would it not be?
Yeah, I mean, it's not. This is not what I meant. Is this is not the whole argument. This really is a physically different metric than.
Yeah, but not isometric, but it is.
Yeah, there's no diffeomorphism you can apply to the original vacuum space-time and get that. So none of these actually are problems for any specific proposal for distinguishing matter from geometry. They're just things to make the pick. They're just kind of random difficulties and problems that are associated with the idea that on some ways of conceiving of these things, it does seem like matter and geometry naively conceived of are fungible with each other, which is potentially problematic given your views on what fungibility may or may not imply for this kind of issue. Moreover, in the same vein, I think if Unruh radiation, for instance, if the Unruh effect is related to excitation of spatiotemporal or geometrical microdegrees of freedom, as one may expect, depending on one's view on, again, on the equivalence principle, on how one characterizes and drives the Unruh effect, and other issues like that I don't have time to go into. But one may also expect it based on certain programs of quantum gravity. And we're just really dealing with the standard Unruh, the traditional standard Unruh effect in Minkowski spacetime, with a quantum field, in its Minkowski vacuum state. Then this already may suggest that the distinction between matter and geometry is breaking down pretty severely in Minkowski spacetime, which would be, I think, really puzzling and worrying. But this is rather speculative. I'm not going to say more about it here. In the if you buy the idea that these kinds of considerations based on fungibility are serious or worth it, or are pointing at something non-trivial, this may in fact suggest that matter and geometry are just different manifestations of an underlying unified entity, like the electric field and the magnetic field with respect to the electromagnetic field. I'm not going to defend this idea because I think you probably really have to go to some kind of program of quantum gravity to really try and argue for something like this. And since I don't think we have any principled reason to care about any existing program of quantum gravity right now, I'm just going to put that aside. So here's a really interesting one that I'm really puzzled about. This seems to be a really profound difference between matter and geometry and GR. It makes no sense to talk about changing matter. I'm sorry, it does make sense to talk about changing matter against a fixed metric, test matter. We all know and love test matter. It makes no sense to talk about unchanging fixed matter against a changing metric, a space-time with a dynamical metric. Because the metric is required to formulate the field equations and the stress energy tensor of matter, but not vice versa. I don't really know what to think about this, though. Whether this actually is telling us anything of importance or not. If anyone has any thoughts or ideas about this, I would love to hear it. So to sum up what hasn't worked so far, we've had difficulties suggested by the equivalence principle. We've talked about how matter and gravity geometry can couple to and constrain each other and themselves. We've looked at symmetries of local degrees of freedom. We've looked at possible operationalization. There we go. Possible operationalization procedures for each, difficulty suggested by the seeming fungibility of matter and geometry in various contexts, and an ambiguous observation about the propriety of various kinds of approximations and idealizations of the metric. So let's try some metaphysics, which is a sentence I very, very, very rarely, if ever, thought I might say. But let's try and do it right. Let's actually try and do it in the way that Newton and Maxwell were metaphysicians. So in particular, let's look. I'm gonna look at approaches based on two different criteria to trying to distinguish geometry from matter. So one, I'm going to look at a possible way to characterize the difference between substance or an accident, or if you don't live in the Middle Ages, body and physical system versus property or quantity associated with body and physical system. And the second will turn on a deeper analysis of how matter and geometry do in fact couple in general relativity with a focus on stress energy. So let's look at substance versus accident. So consider, let's for the moment stick to classical Newtonian physics. Consider inertial mass. If I had to say, here's a physical system and it has inertial mass, I told you almost nothing about the system because every classical system has inertial mass. It doesn't determine the kind of system you're dealing with. In fact, if I say there's a classical system, it has shear stress. I told you a little more because not every kind of classical system has shear stress, but a whole lot do. I mean, the most viscous fluids, elastic solids, a whole bunch of classical systems have shear stress. So there never seems to be a single aspect of a classical system, for lack of a better word, such that to know the details of that aspect determines the kind of system it is. Staying in classical Newtonian physics for the moment, now instead of just telling you what kinds of properties a system may have, let's get a little more concrete and detailed and say that I'm actually going to tell you not only the kinds of quantities, but the values of the quantities that they have. So let's say it is the case, to the best of my knowledge, that for every kind of classical physical system, in general, to know the value of every single one of its physical quantities, to know the type and the value of every single one of its physical quantities, except for one, at a given instant, does not allow you to determine the value of that last final quantity. If I know the position and velocity of a Newtonian particle, I don't know its acceleration at a moment. If I know the value of a Navier-Stokes fluid's shear and bulk viscosity, its mass density, its flow velocity, its flow acceleration, and its isotropic pressure at an instant, that I can't tell you the value of the shear stress tensor. And on and on and on and on. There never seems to be a single aspect of a classical Newtonian system, such as to know the details of that aspect completely tells you the values of all the rest of the system's quantities. And that is why for systems treated by classical Newtonian physics, I think such things ought to be thought of as properties, accidents of physical systems, or quantities associated with them. They're not physical systems in and of themselves. The shear stress is not a physical system, property of a physical system. And in fact, classical physics does not appear to admit a representation of substance, the thing itself and the entire thing, in any reasonable sense. There's no explicit representation of point particle, rigid body, fluid, pendulum, spring in classical physics. You just get a list of properties. So stuff that in your pipe and smoke it. Field theories, however, even classical ones, are different. So consider a classical Maxwell field in vacuum. The Faraday tensor determines every other quantity associated with the Maxwell field. It determines field intensity and flux, stress energy. If you move to a 3+1 decomposition, it tells you energy density, Poynting vector, shear stress, amplitude and frequency of the magnetic and electric fields, or a radiative Maxwell field, you get frequency and wavelength and wave number, you get polarization. And when it's coupled to external sources, you get, the 4D charge distribution. You know the Faraday tensor, everything. And in fact, even if there's not just charge distribution around, if there's some pervasive medium, some dielectric, say, that the Maxwell field is interacting with, the properties of that, of that matter, of that dielectric, its spatial configuration, its permittivity, conductivity, susceptibility, permeability, on and on and on. Then you can calculate further behavior properties of the Maxwell field. Its wave, phase, and group velocities, coefficients of reflection and absorption, refrangibility, diffraction, displacement current, etc. So basically, in short, the Faraday tensor determines the entire state of the Maxwell field under all conditions. In the general case, this is not true under special conditions, like when there are really a shitload of symmetries around, or some other conditions you can specify. No subset, no matter how large, of any of those quantities determines the Faraday tensor. I can give you a complete list of those quantities except for one, and that the Faraday tensor will remain underdetermined. And it's the same for quantum fields as well. If you look, if you look at the quantum Maxwell field in QED, it has the same. It has the same features as I just described for the Faraday tensor. So I claim that there's a sense in which the Faraday tensor seems to represent a substance in a way that you just never get a representation of in Newtonian classical physics. It's the Maxwell field. The Maxwell field is a thing in a way that shear stress of an Avery-Stokes fluid is not a thing. It encodes, but it's not encoded in all the quantities associated with the Maxwell field. So I propose, a criterion for being substance-like, for being a body or a physical system, is that in the formalism of your theory, there is one entity, one symbol, if you like, that encodes, that allows one to recover all features of the system relevant in the regime that you're studying the system in. Now, turning to look to GR, on this criterion, it looks very much like the Einstein tensor is substance-like and TAV is accident-like. Because to know the value of the Einstein tensor determines, in general, the metric, and so essentially everything about the space-time. I say in general because it's actually still an open problem to give necessary and sufficient. If I give you an Einstein tensor to give necessary and sufficient conditions for when that actually uniquely determines a metric, but let's put that aside. As far as we know, those are rather pathological, exotic cases when it doesn't happen. If I know only the values of the stress energy tensor in general, that doesn't even tell you what type of field you're working. Because in perfect fluids, Maxwell fields in certain states, Dirac fields can all have the same value of stress energy tensor. If I just give you a stress energy tensor, in general, you have no idea what kind of field it's associated with. And if we really are to think of the Einstein tensor as substance-like, then I think I cannot resist giving the final word in this section to Arthur Eddington and his very wicked pen. So this is from his magisterial mathematical theory of relativity. If we are to surround ourselves with a perceptual world at all, we must recognize as substance that which has some element of permanence. We may not be able to explain how the mind recognizes as substantial the world tensor, by which he means the Einstein tensor, but we can see that it could not well recognize anything simpler. There are no doubt minds which have not this predisposition to regard as substantial the things which are permanent, but we shut them up in lunatic asylums. I love that. If you can't recognize that the Einstein tensor really is substantial in some important way, you're batshit crazy, and it's off to the loony. He had very high standards for sanity, apparently. So let's look at the metaphysics of matter and space-time geometry. Again, this time the second criteria, looking at stress energy and a somewhat deeper analysis of how it is that matter and geometry naively conceived a couple with each other. This is where most of the technical material is that I'm going to skip over very quickly. So if you have questions about it, please bring it up in Q&A. So part of the way that one characterizes a kind of physical system, is this a Navier-Stokes fluid? Is it a Maxwell field? Is it an elastic solid? What is it? Is characterized in part by the fact that it interacts with other types of systems by couplings of different forms and strengths that are fixed unambiguously for each other type of system. And what counts as a coupling is characterized in part by the physical dimensions of the coupling coefficient terms appearing in the constitutive interactive relations. So consider two of the Maxwell equations. C is dimensionless. I'll explain that shortly. And so the electric and the magnetic field don't couple each other. They don't interact with each other in any interesting substantive way, precisely because C is dimensionless. They're just different manifestations of the underlying entity in FAB. The permittivity, however, of the vacuum, let's say, or a dielectric, if we're dealing with some non-trivial matter, is dimensionful. I claim that the electric field and the charge density do couple with each other in the sense at issue. They are different types of matter fields, or in this case, I claim a matter field and a property of a matter field that really do interact in a non-trivial way. And I claim that one important sign of that is that here the only coefficient is dimensionless, and here the only coefficient is dimensionful. So I'm going to propose the following as a necessary condition for geometry, which I will then spend some time motivating after I propose it. Not very much time, because I don't have very much time left. I have 5 minutes left. But we'll get there. So I claim that all the terms that are going to count as geometry, so of course, at the end of the day, this is the one we're interested in, lambda GAB. All the terms that count as geometry must have the same physical dimension without modification by multiplication by various dimensional constants term by term. Because geometry should couple en bloc with all other fields in the same way, on pain of there being different genera of geometry in a rather radical sense. And this can be motivated in part, by the equivalence principle, and it can be motivated in part by the idea that the left-hand side should entirely arise from the same type of physical entity. But I'm going to say more to motivate, especially that second one, now going forward. So as was already mentioned and adverted to in the previous talk, although I'm not going to make it a necessary condition, but I think it is a fundamental and characteristic property of matter, irrespective of exactly whether one wants to treat that as a meaning necessary condition, is that it possesses stress energy. And so some entities may possess quantities similar to stress energy and very energetic like quantities, but not representable by a tensor, and so not completely localizable. I personally think there's no reason in the world not to associate energetic quantities with gravitational radiation. But again, you don't have to get so exotic if you don't want to. Heat is not a localizable quantity, but it's manifestly a form of energy. You can't have conservation of energy without it. Work is not a localizable form of energy, but you can't have conservation of energy without it. So not all really, really important energetic quantities need to be localizable in a strong sense of being represented by a tensor, which is like the most local thing you can have in, you know, in the kind of differential geometry that's used in general relativity. It's a tensor is a multilinear operator on some tensor product of, you know, tangent spaces and cotangent spaces over a point. That's as local as you can get. So all stress energy ultimately will be included in 8 pi gamma TAB. I'm now including the Newton's constant for reasons that will become clear in a moment. So whatever else is the case, whatever we want to think of as stress energy, it ought to have the physical dimension of stress energy. This can come about by, if you like, multiplying a kind of bare TAB by a dimensional coupling constant, possibly different for each type of matter. But I will tell you in a minute what I mean by have the physical dimension of stress energy. At least I'll give you the necessary condition for it, which is all I need. So there are various properties of TAB, which are all really interesting, but I'll skip over them again in the interest of time. What is really important is that all forms of stress energy are in principle fungible. Any form of stress energy can in principle be transformed into any other form. By physical dimension, and this is now the really important part. In general relativity, it's quite natural to use what are called geometrized units. And what this means, and crudely speaking, this is a way to reduce all physical units for all quantities to one basic unit. So, for instance, I'll take time as my basic one. Now, I might define one unit of time as, say, the time it takes light to traverse a proton's diameter. I can do it in a lot of different ways. I just have to have some reason to think that what I'm latching on to is a universal property of time, or something that will always return the same value of time no matter where and when I measure it, so to speak. Then if I multiply the metric by a constant, that rescales the measure of time in a fixed way. I change my units. And so this is actually not in a logical order. I apologize. This should be, I should have said, given my definition of time, I can now define length and mass in such a way. I can define length and mass using time. So, for instance, my unit of length is just going to be the unit that light travels in 1 unit of time, say, and my unit of mass may be the Schwarzschild radius. I'm sorry, the Schwarzschild mass of a black hole whose Schwarzschild radius is 1 unit of length. There are more complicated and interesting and possibly physically more substantive ways of doing it, but those work for my purposes, just to give you an idea of how one defines these units in terms of each other. It then turns out that multiplying the metric by a constant rescales the measure of time in a fixed way, and give the ways I just defined length and time, length and mass based on time. It turns out that how time rescales, the unit of time when I multiply the metric by a constant, the units of length and mass rescale in exactly the same way. And I'm not going to. And so all other units derivable therefrom, and we have reason to think that every kind of physical quantity can be expressed in units that are composed out of length, mass, and time. You can character a necessary condition then for a quantities having a given physical dimension, say the dimension of time or the dimension of stress energy, is that when you multiply the metric by a constant, it rescales in a particular way. And in particular, stress energy remains fixed under constant rescaling of the metric. And this is easy to see. If you do a simple calculation shows the Einstein tensor actually remains unchanged when you multiply the metric by a constant. Newton's constant remains unchanged when you rescale because length, mass, and time all rescale the same way. And there's a power of 3 up here and there's power of 3 down there, so it just cancels. So by the Einstein field equation, for some quantity to have the dimension of stress energy, a necessary condition is that it remain unchanged under fixed rescalings of the metric, under changes of your unit. So where I'm headed is the claim. It is a theorem that based on all of this that captures the idea that there is no gravitational stress energy tensor. And this is where all the technical details start coming in. And I'm going to skip over almost all of it. So I'll just say that very quickly, the idea of a concomitant is that if you have a tensor, is that it's a tensor that is an invariant function of other tensors. And that's actually a little tricky to make precise. It's a mapping from a fiber bundle to a fiber bundle that basically respects the natural action of diffeomorphisms. And if there is a gravitational stress energy tensor, it ought to be a concomitant of the metric or Riemann tensor. It ought to be an invariant function in some sense of the metric or Riemann tensor. And I go through several argumentative steps to get here, but I claim the only viable candidates in the end for a gravitational stress energy tensor are two covariant index of second order 0-weight homogeneous concomitants of the metric. Don't worry if that makes no sense to you. All you really need to know is that it should be something that looks like an Einstein tensor, more or less. That doesn't vanish when the Riemann tensor doesn't vanishes, and that has vanishing covariant divergence when there's no stress energy around. And then it's a theorem that there are no such things. And a different interpretation of this, though, so that by itself may make you think, geometry can't be matter, gravity can't be matter because it has no stress energy tensor. But there's a different interpretation of this theorem, which I also quite like, which is that it can be an expression, if you like, of the uniqueness of the Einstein field equation under certain constraints on what a gravitational field equation can look like. Just like Lovelock's classic 1972 theorem is often invoked in the same way. The theorem is stronger than Lovelock's in certain ways, but the most important part for our purposes is that I think that the assumption of having dimensions of stress energy is really physically perspicuous and completely relevant to our project, because all other terms constructed from the Riemann tensor and other geometrical entities, and you take any quantity constructed from the metric, topological invariance, anything you want, what this theorem tells you is that no matter where you put it, left-hand side or right-hand side, because as Niels pointed out, you can always move shit around. In order to get the physical dimensions consistent, any other quantity that you construct from kind of manifestly geometrical objects has to be multiplied by a dimensional constant for consistency. No other thing you can construct out of any geometrical structures will have the physical dimension of stress energy. Thus, by the earlier argument, I claim any such term that you construct from the Riemann tensor and other geometrical entities ought to be considered a stress energy tensor for perhaps an exotic matter field, and so put on the right-hand side. And so in particular, lambda GAB ought to be put on the right-hand side. I'm going a few minutes over. I apologize. I'm almost done. So in general, any such term that requires dimensional full coupling constant, whether concomitant of the Riemann tensor or not, I claim ought to be put on the right-hand side of the Einstein field equation and considered to be a stress energy of a form of matter in the framework of GR, if you buy my interpretation of that theorem. I conclude with the aporia. And a lovely quote from Bertrand Russell. To the philosopher, the difference between matter and empty space is, I believe, merely a difference as to the causal laws governing succession of events. not a difference expressible as that between the presence or absence of substance, or is that between one kind of substance and another? I'm not, and the context of this quote is a little delicate because he does in fact contrast this with the physicist's position. And I'm not really sure where I fall on this. So I've given you two criteria for being substance-like, matter-like. I haven't told you what the relationship between being a substance and being matter is, but there seems to be, at least traditionally, a rather close and intimate one. Neither one has any obvious problems that I can see, like all the abortive attempts I went through. So the obvious question asked now is, how does the criterion for being substance-like square, if at all, with the criteria based on coupling constants and stress energy? Do we need them, in fact, to deliver the same verdict? And if they don't, is each capturing something perhaps orthogonal to the other insofar as, for example, geometry may also have substance-like properties or aspects or features? Prima facie, lambda GAB tells you the metric up to a constant, so it tells you everything about space-time. So it seems like a substance, according to my first criterion. So let's put it on the right-hand side. But I've already argued that since lambda is if one thinks of lambda as a dimensional coupling constant, because GAB, the metric does not have the dimension of stress energy, physical dimension of stress energy. So we ought to think of this as a stress energy tensor, and we should put it on the left-hand side.